Thank you, Martin. Thank you, organizers. I'm going to very briefly tell you about what's going on the ground. And I'll go a little bit quickly. If I mix up something, please come find me later on. I'd be happy to talk some more about it. So I'm speaking on behalf of Einstein Telescope, Cosmic Explorer, LIGO Laboratory. I want to note up on this first page and probably a couple other places the great support we have from the US National Science Foundation. It's what makes all this stuff happen in the US. So this is the kind of plot that you've been seeing at this meeting in several different times, and I want to add a red dagger and talk a little bit about why the terrestrial instruments are stuck up in this corner of the spectrum, which of course gives us more value and need for these other approaches. So why are we limited to frequencies above about a hertz or so? Let's review the basic notion here. A passing gravitational wave will shorten the light path for one of these arms and lengthen it for the other one of these arms. We choose about 90 degrees for the LIGO instruments at least. And the effective length change is scaled by the length of the arms times the gravitational wave strain. And so we turn that, this is a transducer that changes those differences of length into changes in light intensity and thus into photocurrent, then into voltage, and then onward to your laptop. The readout is limited by quantum effects ultimately, but the physical motion of the mirrors due to local forces masks the minuscule changes from gravitational waves, much in LISA at low frequencies, and that's what we battle against. So there's this Newtonian background. As seismic waves pass by our instrument, the distribution of mass changes as a function of time. And if you want to think like Newton, that the gravitational attraction varies as a function of time. If you want to think like Einstein, space is warping dynamically in time. At any rate, that causes our test mass, which should be isolated from all external forces, to move around in a way that we cannot shield. We can do a really good job of seismic isolation with fancy seismic suspensions and active isolators, but we can't keep that motion from the Newtonian background away. And that's got a spectrum. If you look at a likely sensitivity curve of a gravitational wave antenna versus frequency, and this is 1 hertz, this is 10 hertz, there's this wall which is falling at something like 1/f⁵ that effectively prevents one from going any higher, any lower than about a hertz. This is the kind of good sensitivity that you get at the best level. If you say you don't want to have, you want to be able to see up to about a decade below your best sensitivity, that puts you at 3 or 4 hertz, something like that. There's no way around that. This is another example of a whole bunch of instruments that you could imagine building, and they just stop at around 10, 9, 8, 7 hertz. So it's the ultimate limit on the lowest frequency of detectors on or underground. And so it also limits, for instance, the largest black holes that you can hope to see, because they'll coalesce at frequencies, larger ones will coalesce at frequencies below this masking force that we have. So let's talk a little bit more about more practical limitations to the terrestrial detectors. Well, I said arm length, you want to make the arms just as long as possible to make the effective length change as big as possible. Currently, that's at 3 or 4 kilometers. There's an optical resolution of looking at the difference in phase between the 2 beams that are returning. There's statistical uncertainty and photons, Poisson statistics, shot noise, if you will. And that's something, the shot noise limit gets better as you make the instrument longer and longer. It also gets better as the square root of the power. On the other hand, if you put too much power in, the photons impinging on the mirror will cause it to shake, and it's a white force, so that the motion goes as 1/f², and that leads to a limit in the strain sensitivity, which, as I said, 1/mf², still getting better with the length, but it gets worse now with the power as it increases. So you can see that there's for a given frequency, there's an optimal power to get a given result. And we're operating at that limit or even beyond it in some places, at around 100 watts of laser power. So it may be an obvious thing to say, sensitivity improves the signal rate, a thing that is striking for astronomers who are used to thinking of signals falling off as 1 over r squared. We detect the amplitude of the gravitational waves. So if you increase your sensitivity by a factor of 2, you see 2 cubed more sources. It's a really nice return on improvements in the performance. And so as a consequence, as we go from measuring epoch to measuring epoch, these are days of observing versus the number of candidate events, as we improve our instruments, the slope here improves, and to aid the eye for the most recent run that we're now in which we're now the middle, you can see there's this further improvement. That improvement takes time. Between 03 and 04, we spent a year and a half. Well, there were some other things that happened in those magic years. But at any rate, it's really a good return on investment. And to date, even though we take time away, the number of events that we get after improvements is more than if we just left the instruments observing. So what are we doing in the bigger scale of things? LIGO, Virgo, and Kagra cooperate very closely in observing. We have a timeline which starts back here in 2015. That was a good year. And this one runs up to 2030. And so we're currently in 04. We're about maybe 2/3 of the way through 04 now. We planned another set of modest improvements to the instruments here, with perhaps another as much as a factor of 2 improvement in the sensitivity. These are these distances to a binary neutron star in spiral, signal-to-noise ratio of 8, averaged over polarizations and directions in the sky. We will be proposing soon a final upgrade to the 3 and 4 kilometer instruments, which would be implemented in the 2030s. Let's take a look at what that looks like for LIGO. So as you can see, we're now currently in 05. And I'm sorry, we're now currently in 04. We will make some modest improvements and then start up 05 sometime in 2026. Meanwhile, we're starting to work on something we call the A-sharp design, which is still using some of the fundamental parts of the advanced LIGO instrument, but then bigger mirrors, more laser power, lower losses, with the idea of having something ready in the early 2030s. And the notion is that this instrument, another factor of 2 better, would run until the next generation of observatories is ready to observe. So what could you do if you had an even yet better detector, like a 10 times better detector? I won't say much here because Somaya Nisanki is going to talk in just a couple of minutes. But obviously, it would increase enormously the number of sources that you see. It would be many sources per day. It will improve localization for multi-messenger astronomy. You'd be able to see much further than the telescopes, but even for closer objects, we'd have much higher SNR and thus better localization. That better SNR allows us to make more stringent tests of general relativity. We expect to make instruments with a wider bandwidth. The neutron star coalescence final phase emits signals up in the several kilohertz region, where we currently don't have very good sensitivity. We'll be working hard to improve the sensitivity there to be able to learn more about what happens in that very dense matter. And this is a nice graphic for this. We're in the center here. Here are a couple of our events. We're currently observing in 03, and we have, in 04, which is between 03 and A+, I'm sorry. So we can see out to a redshift for the neutron star binaries of a little bit more than 1. With a factor of 10 better instrument, we could see out to redshifts of 10, and that starts to include all of the coalescences of objects that are within our frequency range, which is binary black holes up to maybe 500 solar masses, and then neutron star binaries. So it is a complete map of the things within our reach and complements the complete map that LISA will make for much more massive systems. So how do we do that? The most obvious thing to do, the brute force approach, is to make a 10 times longer instrument that will give a 10 times larger signal. Now, why does that work? Well, the noise due to stochastic forces is independent of length. That Newtonian background I discussed is the same whether I've got 2 masses 10 centimeters apart or, kilometers apart or tens of kilometers apart. If they're right next to each other, they could be, it might be less, but good, never mind. Also unchanged, the seismic level, thermal noise motion, magnetic and electrostatic dynamic forces, a lot of the same kinds of things that disturb LISA at low frequencies. And that works up to the point where you get to about 1/2 of a gravitational wavelength. And for our frequencies, that means that we could go out to hundreds of kilometers if we could do it reliably and sensibly on the Earth's surface. It turns out actually for neutron stars, because you want to get higher frequencies, shorter wavelengths on the ground, probably 20 kilometers is better than 40 kilometers. But at any rate, having a longer instrument is a good idea. One other thing about that is that the sensing noises also improve even faster. It's not just 1/L, it's better than that, because the shot noise gets better as the square root. The radiation pressure noise, that photon pressure noise, gets better as the 3/2 power. Similarly, the coding thermal noise and the residual gas noise, the polarizability of the remaining molecules that are in the vacuum system that we use to transmit our light. We have to buy our vacuum system, at least it pays for it otherwise. But anyway, all of these things get better as you make the instrument longer. So that leads us to the US proposal for next generation instruments. And once again, I want to note that the National Science Foundation is our robust supporter. So Cosmic Explorer is designed to be a larger and more technically advanced version of LIGO. We're basically taking the concepts that have worked so well in LIGO and extending them to a longer baseline with some new technologies. We would like to build two installations, one with 40 kilometers and one with 20 kilometers. It's a LIGO-like concept for a single interferometer per site on the Earth's surface. Einstein Telescope is taking a different approach there. And we intend this to be part of the network with Einstein Telescope and perhaps any other remaining terrestrial detectors in the 4-kilometer range. If you want to learn more about this, take a look at cosmicexplorer.org. You can find, among other things, this document, but a great deal more information about where we are and where we're going. cosmicexplorer.org. So what's the status? Our conceptual design is now underway. Well, I have to say, we don't yet have preferred sites. There are many, many places in the US where you can lay out 20 or 40 kilometers. And in particular, what you don't want is a flat site, or you want a truly Euclidean flat site, which you would normally talk about as a bowl. But if you do topographical surveys, you can find places where relatively little Earth would have to be moved to make a truly flat trajectory for the laser light and the vacuum system that enshrouds it. So that's one of the things that we're doing. A really important complement to the simple geographical searches is that we want to fit into the host communities. We've seen, and I think TMT and Mauna Kea in Hawaii is the classic counterexample. If you need to really integrate the activity into the communities where you're situating them, especially something which is on the surface and tens of kilometers long. We want to work very closely in the US with indigenous communities to make sure that they're comfortable with us joining their endeavor to the stewardship of the land. The Cosmic Explorer has got funding approved for this conceptual design phase. And our next phase is in discussion with the NSF. We have some international contributions from the UK, Canada, Australia, and Germany. Big news in 2024 for us is that a blue ribbon panel, chaired by Vicky Caligara, made it very clear that the US should pursue a next generation instrument, and something in all of the networks that they thought would be good to, with which to proceed is the 40-kilometer Cosmic Explorer. In fact, their favorite network was an interesting one. It was Cosmic Explorer at 40 kilometers, Einstein Telescope, the next page, and LIGO India, which is, we have an extra advanced LIGO detector sitting in boxes in Hanford, Washington, and it will be shipped to India as soon as a vacuum system is prepared there, and that would actually make a very good network, even though one of the three legs would be much less sensitive. And then there are other kinds of combinations that work well. Our goal is to have these observatories running by the mid-2030s, and so be able to pick up the gauntlet from the current 3 and 4 kilometer instruments. In Europe, the vision is for Einstein Telescope. Its notion is to build underground in some measure because so much of the surface of the ground in Einstein Telescope in Europe is covered with people and cows and stuff. The idea is to make a more subtle, rather than the brute force American approach, typical of the US, I guess, Europe wants to do something a little bit more subtle and be more challenging in terms of the technology that's adopted. And so the idea is to make separate high-frequency and low-frequency detectors, some of which use cryogenic test masses to reduce thermal noise, some which use very high power to get better resolution. It's intended to put it underground, which does reduce the Newtonian background. It allows you perhaps to move, I'll say some numbers that may make some people in the room mad. Maybe you'll go from 7 hertz to 5 hertz is the lowest cutoff frequency, but it will be quieter there, and that's good. Whoops, let me go back. The current envisioned time frame is kind of matched with Cosmic Explorer, or Cosmic Explorer is matched to this, if you will. The notion is to commence science operations sometime in the 2030s. Its status, well, it's a fully recognized European project in the European Strategy Forum for Research Infrastructures, or ESFRI roadmap. And that was key to getting some funding identified. And the remarkable thing is to hear that were it to be built in the Netherlands, there'd be something like 10 to the 9 euros available. Were it to be built in Italy, a similar number. And that's a great deal of progress. We don't know how to get there in the US yet. Site evaluation is well underway, and specifically there are a couple of sites in mind. There's one which is, you can't think of something more European than a site which has got one leg in the Netherlands, one leg in Belgium, and one in Germany. Or Sardinia, which has a lot of advantages as a site as well. There's some potential for a site at a new astrophysics center in Germany. I think that's still in discussion. It's a complex task, obviously, to find the best site. Geophysical and environmental questions come up, financial organization aspects, what kinds of services and infrastructures are around. A lot of similar questions to the ones we pose in the US, but perhaps not so much a stress on the indigenous community. So what's the reach of these instruments? These are the last couple of slides. This is a kind of plot we've seen before from the Big Bang to today. The current instruments are looking out here at a redshift of maybe a couple. By 2033, the best that we think we can do in the 3 and 4 kilometer environments is at a redshift of probably 6, 7, 8, something like that. With these new instruments, Cosmic Explorer and Einstein Telescope, we can see back to the dark edges, see back before these things had accumulated into clumps. And of course, LISA would be there as well. So with that, I hope to have convinced you that ground-based gravitational observation works. Samai will tell you a lot more about the interesting science that can be done. Lots of sources yet to be observed. The scaling laws show the technical feasibility of even better detectors than the current ones. US concept of the Cosmic Explorer, these 2 sites on surface construction using basically LIGO as the baseline. The European concept is using multiple interferometers underground and pushes detector technology as an alternative to brute force. We're both eager to participate in multi-messenger astrophysics, and of course, we're looking forward to those few multi-band sources with LISA. Thank you.
Thank you, David. We've got time for a few questions. Do we have any? Yeah, it's hard to see in the lights over here.
All right, thank you so much for your talk. The question is the following. Suppose we could choose, and suppose we want to have maximal science yield. So what is the best order of the missions to appear? If you choose Cosmic Explorer, LISA, Einstein Telescope, and maybe Tianjin, or something decihertz. I mean, so in which order is best for the missions to come up? At the same time, one before another? I mean, so what's your opinion about that?
So I think I heard the question, what is the best order for these instruments to come alive?
Well, to maximize the science yield, that's right.
Yeah, right. Well, I think the value of the terrestrial interferometers is enormously multiplied by having a network. I think, as a lover of general relativity and searches for defects in the general relativity, I think a single detector can do a lot of interesting stuff, but the communities are too small. And you have to be able to reach the astronomical community. So it almost makes no sense to have a single one of these detectors come up. You need to have at least pairs and probably a triple of good instruments at comparable sensitivity. I think it's an interesting question whether or not coincidence between LISA and the ground-based instruments is of great value. I think the estimate for the number of multi-band sources has varied, but mostly gone down since the ideas were first realized, floated a few years ago. And then the other thing to say is that you can always work your way back, for instance. Should the Einstein Telescope and Cosmic Explorer come online after LISA flies, you could then use the final coalescence that you see in 2050, calculate back and look at the data that you had in the can from LISA, and infer additional science from the LISA data. So I think you could go in either way. I think that order is probably better than the converse to have Einstein Telescope. But the other thing to note is that It's always a really striking thing to me, the fact that space missions are limited in duration. These Einstein Telescope and Cosmic Explorer are projected to have 50-year lifetimes. And so there should be some overlap between a number of space missions, the second generation LISA and so forth and so on, and these things. So.
Thank you.
Thanks, David. I think we've got time for one final question. Janway over there.
Okay, David, so sometimes I think about Decigo. So, with C, you can see actually further away, but you still get only half the waveform in some sense. So have you ever think about move LIGO into space?
So the question is about Decigo and how it fits into the picture. I think the most interesting place in the gravitational wave spectrum is actually between LISA and the ground-based instruments. There's a little chance that there's a minimum in the gravitational wave static there, and it gives you a better window into a possible detection of a cosmological gravitational wave background. Decigo is an extremely ambitious proposal to build multiple triangular constellations in space of LIGO-like locked interferometers. It's a wonderful concept. I don't know if that's the best way to get to that frequency range, but it's certainly something to try to pursue.
Thank you. Let's thank David again.